Hello and welcome to Twistor's Explain series. In these series, we will give a more informal or brief overviews of various mathematical concepts or areas. In this video, we're going to take a look at the integral, or more specifically, the definite integral. Let's get to it. If we have a function, f of x, we can make a graph of that function over an interval. Let's call the starting point of the interval a and the ending point of the interval b. Now we might ask, what is the area of the region underneath the graph on this interval? This is precisely what the definite integral tells us. So how is this integral constructed? For starters, we could approximate the area by making a bunch of rectangles, each of the same width, which we call delta x. Together, these rectangles cover the original interval from a to b. That is, the interval is now divided up into equally large pieces. In this case, we've chosen 6 rectangles, so the width delta x of each rectangle is the length of the interval b minus a divided by 6. You might protest already and say that this is a bad approximation, since we are obviously missing some of the area under the graph, and some of the rectangles stretch above the graph as well. But hold on, because the height of these rectangles is not chosen at random. In fact, the height of the first rectangle is precisely the function f evaluated at the beginning point of our interval, that is, f evaluated at a. So what is the area of this first rectangle? Well, the area is the width of the rectangle, delta x, times its height, which is f of a. In other words, f of a times delta x. As for the second rectangle, its height is precisely the value of the function once we've moved a distance of delta x away from the starting point a. In other words, f evaluated at a plus delta x. So what is the area of the second rectangle? Well, again, it's the width, which is still delta x, times the height, which is f of a plus delta x. So f of a plus delta x times delta x. Let's do one more. What is the area of the third rectangle? Again, it's the width delta x times the height of the rectangle, which is now the value of the function once we moved a distance of 2 times delta x away from the starting point a. So f evaluated at a plus 2 delta x. So the area of the third rectangle is f of a plus 2 delta x times delta x. This pattern continues, so the area of the fourth rectangle is f of a plus 3 delta x times delta x. The area of the fifth rectangle will be f of a plus 4 delta x times delta x. And finally, the area of the last rectangle will be f of a plus 5 delta x times delta x. Adding up the areas of these rectangles, we obtain an approximation for the area of the region underneath the graph of the function and our interval. Now, originally we had 6 rectangles whose width was 1/6 of the length of the interval from a to b. But what if instead we made a finer partition of the interval, that is, we divide into more rectangles, say 12. Now, the width of each rectangle delta x is the length of the interval divided by 12 rather than 6. Just as before, however, the height of the first rectangle is the function evaluated at the beginning point of our interval, so f of a. The height of the second rectangle is again the value of the function once we've moved a distance delta x away from a, so f of a plus delta x. And so on and so forth for the others in exactly the same pattern as before. So now, if we add up all the areas of our rectangles, our sum will have 12 terms as opposed to before, where we just had 6. Note that the height of the last rectangle is the function evaluated once we've moved 11 times delta x away from a. That is, 1 step less than the number of terms in our sum, just as was the case before. As you might have noticed, the area that we were missing before has shrunk, and our approximation has gotten more precise on account of the finer partition we've made into more rectangles. But why stop here? We might continue by considering more and more rectangles, each of them narrower and narrower than before. That is, the width delta x of the rectangles are shrinking. Consequently, our approximation of the region's area gets better and better. Thus, in the limit where the width becomes infinitely narrow, that is, in the limit where delta x approaches 0, we obtain the area of the region underneath the graph. But how do we compute this area more specifically? Well, the width delta x of each rectangle was the length of the interval b minus a divided by n, where n was the number of rectangles. Earlier we started off with 6 rectangles, so n was equal to 6, but in principle n could be any number. Thus, since we are dividing by n, making n larger and larger is the same as making delta x smaller and smaller. That is, approximating by more and more rectangles, the width of each rectangle gets narrower and narrower. So taking the limit delta x goes to 0 is the same as taking the limit n goes to infinity. Now, when adding up the areas of all of our rectangles, we start off with the area of the first rectangle, which, if you recall, was f of a times delta x. Replacing delta x with b minus a over n, this is f of a times b minus a over n. We then add the area of our second rectangle, which was f of a plus delta x times delta x. Again, replacing delta x with b minus a over n, this is f of a plus b minus a over n times b minus a over n. For the third rectangle, the area was f of a plus 2 times delta x, and again we can replace delta x with b minus a over n, so we get f of a plus 2 times b minus a over n times b minus a over n. And so we add more and more rectangles, until we get to the last one, which, if you recall, was the value of the function f once we moved n minus 1 times delta x away from a times delta x. We can write this sum a little more neatly using the summation sign. If you haven't seen this symbol before, then don't worry about it. It's just another way of writing the sum that was on the screen before. Finally, we take the limit of this sum as n goes to infinity, meaning we are now summing the area of infinitely many rectangles, all of them infinitely narrow. This type of infinite sum is so special that it deserves its own name and symbol. It's the definite integral of the function f over the interval from a to b. This is symbolized by the integral sign, where the limits, meaning the starting and ending points of the interval, are indicated. Inside the integral, we write the function f that we are integrating, and finally we have the differential dx, which tells us what variable we are integrating over, in this case x over the interval from a to b. Somewhat informally, you can think of the expression f of x dx as the area of infinitely narrow rectangles situated at each point x on the interval, which we are then summing up. This is the definite Riemann integral, and it gives us the area of the region in the plane, bounded by the graph of the function f, and 2 points on the real line. If you like our content, please subscribe to my channel.